So Tomby is going to describe the Basin and Petroleum system model for the Jeanne d'Arc Basin, offshore Eastern Canada. And then after the break, she will talk about something that I think will be novel to this group, which is exploring or optimizing exploration decisions. And perhaps that's not something that we typically think about as basin modelers, geochemists, structural geologists. Often that gets handed off to other teams, right? So hold on to your seats for that. It's going to be a tour de force. But first, because that is based on the model, the Jeanne d'Arc Basin that she created, she will start with that part first. And take it away, Tanvi.
Thanks, Allegra. First, I apologize if there is any background noise. I have to take this call from a hospital, but hopefully the headsets make the audio clear. All right, so good morning, good afternoon, and good evening from wherever you are right now. And I'm going to talk about probabilistic resource assessment in this first talk. I'm going to spend about 3 minutes on the overall goal of the thesis, making a case for what can improve in current basin modeling workflows and why you'd be interested in how Bayesian networks can bring improvements. Then I'll spend a quick few minutes on the geologic background of the Jeanne d'Arc Basin because I want to demonstrate how the methods I propose can be applied to other real basins. But I really want you to focus on the workflows because they can be applied to other areas, perhaps the ones you are working on right now. Then I'll discuss how we were able to model more accurate hydrocarbon accumulations by examining time-varying permeability behavior of faults, by decreasing the uncertainty in timing of fault closure using pressure and volume data with Bayesian networks. Then I'll wrap up with how modeling using a range of uncertain parameters and then narrowing down using well data helped us better assess accumulation volumes. And then we'll go on to value of information and decision optimization in the next talk. All right. So a classical approach to evaluating exploration decisions using basin and petroleum system modeling starts with modeling a few possibilities and involves manual updates to the models with the goal of a better answer instead of an accurate assessment of uncertainty and its impacts. And economic considerations and execution decisions are exported typically to a separate team or a third party. A holistic approach, on the other hand, would involve considering a wide prior uncertainty, then systematically updating the models with new data. And then geologic, reservoir, and production engineering evaluations would ideally be integrated with economic decision making with lossless handoff of uncertainty information. And what I mean by this isn't that a geologist should also be an expert in economic evaluation, but that their detailed uncertainty understanding not be boiled down to a simplistic single number like probability of success. That the interdependencies between elements should ideally be quantitatively communicated. So for example, if we drill prospect A, it doesn't just tell us about prospect A, but it also reduces uncertainty in prospect B and C by X%, and hence could be more valuable. So let's try to apply this approach to a real basin called the Jeanne d'Arc. And again, this topic focuses on this first part, and then we'll see the next two parts in the next talk. The Jeanne d'Arc Basin is located offshore Newfoundland in eastern Canada and has produced 1.8 billion barrels to date. This is the outline of our model and the four major producing fields in the basin. Two major rifting episodes have affected the tectonic evolution of the basin. First, in the Triassic, the breakup of Pangea supercontinent and decoupling of North America from Africa led to the formation of half-grabens bounded by novel faults. And then marine incursions from the Tethys Sea into the Rift Basin led to the deposition of evaporites. Then thermal subsidence that followed the rifting event created accommodation space for deposition of fine-grained siliciclastic and carbonate sediments in the early to middle Jurassic. known as the Downing and Voyager formations, shown right here. Um, and then a gradual reduction in the subsidence rate followed in the middle to late Jurassic when calcareous shale was deposited in the silt basin that was cut off from terragenous input. So the late Jurassic Rankin formation shown here um, has a basal unit of massive oolitic limestone, suggesting a high energy, shallow marine environment deprived of siliciclastic input, and it's overlain by carbonaceous shale, which was deposited in the subsequent marine transgression. So the predominant source rock in the region, which is called the egret member, of the Cambrian age, is a unit in this Rankin formation, and it was deposited in low energy anoxic bottom waters in the late Jurassic. And then the second major rifting episode that began in the late Jurassic and lasted through the early Cretaceous, which was the opening of the North Atlantic, separated Newfoundland from Iberia. So imagine this like as a zipper effect. First the South Atlantic is opening up and then the North Atlantic. And then one of the major features that was being formed in the early Cretaceous due to transtensional forces from stresses from all of this tectonic activity caused the formation of the Trans-Basin Fault System, which is an extensive series of west-northwest, east-northeast oriented faults in the basin. And we'll come back to these faults in the next many slides. So finally, a third rifting event, which was the splitting of North America from Greenland, occurred in the Paleogene, and we don't see much of its effect in the John Dark Basin. And starting in the late Cretaceous, the transition from extensional to passive margin phase created just like a big, a thick sediment column of called, which we group as the Bankaroo Formation, which forms the overburdened rock required for burial-related heating of our source rock. All right, so using all of this information and surfaces derived from seismic data provided by our industrial affiliate, I created a 3D basin model that spans 100 by 80 kilometers and had a 250-meter resolution that I downscaled 4x to get a model with 120 million cells for simulation. And these are some of the lithologies assigned and some organophases assigned to the model. And this one is for the egret, the main source rock. And to that model, I added faults. And here is the zoomed in view of the model. This is the model boundary. This is the transbasinal fault trend that I talked about. And these are some of the major fields. So Terra Nova, Hebron, Hibernia, and White Rose. No published source to date, to our knowledge, has incorporated the study of faults in this basin, but they are extremely important, as you see, to model accumulations because they affect accumulation volume in the three stacked reservoirs, as well as the pore pressure in the reservoirs. They also form important traps for the major fields in the basin. And we know that the faults are impermeable at present day because the wells to the north of the fault trend encounter overpressure, while those to the south here are hydrostatically pressured. The oil water contact depths are also different across the faults. But if we model these faults as impermeable throughout their history, we can't recreate the accumulations that we observe in the reservoirs. So also the hydrocarbon fluids don't migrate up to fill the shallow reservoirs, and the fields to the south of the fault trend don't fill up. So the source rock to the south of the fault trend is poor. So for Terra Nova field, for example, to exist, hydrocarbons must have migrated laterally from the north. But if we, in order to recreate some of these accumulations and pressures, if we model the faults as permeable, then we see that there are very high migration losses, and it also results in draining away of the fields to the north of the fault. So what about something intermediate and more accurate, like shale to gauge ratio? We still don't reproduce the accumulation volumes measured, and we think that this is because shale to gauge ratio can't account for the evolving fault properties over time due to processes like burial and cementation. And I know, so Anatoly mentioned this paper, and some of you might ask, did you try the Spurvik 2002 method, which resolves this by combining the shale to gauge ratio with burial history of the fault and cementation? But that approach requires so much information that often cannot be obtained in regional scale models, and hence it couldn't be applied to our model. But a final thing that we tried worked, and that is the time varying permeability behavior of faults. And this is how we implemented it. So last year, I've talked about the findings from modeling the uncertainty in heat flow and the source rock quality using Bayesian networks. But in that study, the fault closure had three different scenarios, and we saw that those scenario-based methods did not work very well. So as opposed to last year, the thing that we've added now is considering this as a continuous parameter, the timing of fault closure, as opposed to a scenario-based uncertainty. So this is one of the uncertain parameters in our Bayesian network. In red, you see the prior uncertainty, the prior probability of timing of fault closure, and the result would be this posterior probability distribution. So we want to use Bayesian networks because they allow inference despite varying multiple parameters at the same time. So if I were to do this analysis with these uncertain parameters with one parameter at a time, then inference as well as uncertainty analysis would need a number of simulations equal to the number of uncertain variables raised to the power of the number of distinct values of each of these variables, which would be an exponentially large number of simulations. But because the Bayesian networks can encode conditional independence relationships, we can examine these uncertainties with a limited number of simulations. So here's the workflow. We start with Monte Carlo sampling of the prior distributions of our uncertain parameters. We use the Bayesian network graph structure to learn the conditional probability distributions. Sorry, I should have mentioned what this stands for. And then we use evidence data, in which case I used data from 22 distinct wells, which was publicly available in the offshore, Canadian Newfoundland Offshore Petroleum Board website. And I used the vitrinite reflectance, temperature, and pressure data for inference to obtain the posterior probabilities of our model parameters as well as update predictions. And for the fault closure specifically, here are the results from the 120 3D basin models that I created. And we see that the deepest John Dark reservoir volume is proportional to the timing of fault closure. That is, and it implies that the more time it takes for the faults to close, the more hydrocarbons are leaked from the deeper John Dark reservoir to the shallower Hibernia and Avalon Ben Nevis reservoirs. Uh, and also when we perform distance-based global sensitivity analysis, we noticed that some accumulations are very sensitive to the timing of fault closure, while say a parameter like generated hydrocarbon volume is insensitive to the age of fault closure as expected and is mostly affected by total organic carbon and hydrogen index, sorry. So the takeaways from this part are that modeling time-changing fault behavior was very important in this case and might be also very important in many other basins. And we were able to accurately model it and conduct sensitivity analysis while avoiding exponential compute by using Bayesian networks. Um, so I'll talk about how we take this uncertainty analysis to quantitative decision making in the next talk after the break. And I'll leave you with one quote that I like that summarizes the need for communicating not just the expected or best value, but also the uncertainty in our estimate. And it's by Carveth Reed. It's from 1853, and it says, "It's better to be vaguely right than be exactly wrong." Thank you.
Fantastic. Thank you. Tanvi, there is one question for you. So Tanvi, the fault seal methods you apply all address permeability and thus sealing across the fault. Have you considered leakage along the fault? The latter is a topic of effective stress rather than perm, and thus quite different poromechanics. Recall that the chain breaks at its weakest link, and that weak link may not be permeability.
Yes, yeah, I think that's a very good point. Um, I do see effects of permeability still on leakage along the fault, because we saw that filling of the shallow reservoirs was affected by the permeability of the fault. But modeling the using, say, more details about effective stress, that's not something that I have incorporated yet, but I think that could be quite interesting, perhaps more complex. Yeah. Thanks, Eva.
Anything else? We are running a little bit behind on the break. I think if we all get up and stretch our legs, so it's 10:03. We were scheduled to come back at 10:05. So I think that's okay. There are 3 talks left after the break, but we won't go too late for our listeners in Europe. So it's 10:05. Let's gather back at 10:18. Can we do that? 10:18, just to make it interesting. And don't forget, you can type questions in the chat, and you can also type questions and comments into the tiny URL. So we will take a break, and we'll have Tanvi again with decision making. Tanvi has a unique approach here to making exploration decisions, which I think all of you will be very interested in. I should say that while Tanvi has been here at Stanford, she also qualified for a minor PhD in management science and engineering, and worked with a professor over there who has quite an international reputation in this field. And so that will not surprise any of you who know Tanvi well, what a smart and go-getting student she is. So with that, take it away, Tanvi.
Thanks, Allegra. Yeah, so the majority of this talk will focus on the use of influence diagrams for decision analysis. I'll come to what influence diagrams are. We'll get there gradually. And I'll be making the case for why they might be better than the traditionally used decision trees in the exploration decision context, and then demonstrate that application on our John Dark Basin. All right. So we are moving from uncertainty analysis to decision making, and I plan to illustrate how influence diagrams can be used to communicate dependencies among variables studied by different teams in a large organizational setting, and also mathematically evaluate the effect of uncertainties to keep an auditable track of inputs and assumptions and facilitate quantitative and objective decision making. Iswick at 2015, which is Iswick and Professor Tapan Mukherjee here. They're, to my knowledge, I think the only published resource to illustrate the numerical application of influence diagrams to find optimal exploration strategy. And I build upon their work and I illustrate this in a more complex, non-hypothetical example to convey how this method can be applied to real prospects. And note that Brotwald and Begg, who uh, sort of recommended this holistic approach, did recommend influence diagrams as the best way to achieve this, but they hadn't yet illustrated how to go about implementing it on a real basin. So I'm going to start with some very simple examples to show why value of information analysis is not simply intuitive, not intuitively simple. And bear with me as I walk through these, because in the end, you will see why data will be good to obtain is usually not an obvious decision, and human brains might naturally miscalculate it. So in this simple example, let's say that we have evaluated that the probability of finding oil is 1% in this place. And uh, like the first question we'll jump to is why 1% and how did you come to it? This is a simple example, we'll build on it. So just assume that I'm telling you it's 1%. If we do find oil, the revenue from it would be $100 million. And the cost of drilling the well is $10 million. The question is, given this information, will you drill that well? And as most of you might have evaluated, so feel free to grab a pencil and a paper and do this for using your own methods as I walk you through this. The expected value of drilling is a negative $8.9 million because the low probability of finding oil, which was 1%, and given the 99% chance that we won't find oil, hence we would end up just spending the amount on drilling the well. So the other alternative of not doing anything or any action is better with expected value of 0 compared to this negative $8.9 million. So our prior value for this decision that any objective decision maker would make is $0. Now, what if I told you that we could acquire seismic data that perfectly indicates if there is oil or not, and what is the amount that a rational decision maker should be willing to pay for it? Um, so we do this calculation again, and in this case, if the seismic says that there is no oil, we cap our losses to 10 million, and if it's no oil, then we cap our losses to 0, and if it says there is oil, then we go ahead and drill. And that shows us that the posterior value of doing such a thing would be $1 million, and hence the value of information, which is defined as the posterior expected value minus the prior expected value, would be $1 million. So we've established using very simple decision trees so far that if seismic is 100% accurate, it makes sense to pay $1 million. Now, my question to you is, if the seismic was 95% accurate instead, would you pay $500,000? I'm cutting the cost to half, just for a 5% decrease in accuracy. And I'll wait for a quick 5 seconds if anyone wants to either comment yes or no, or show with your thumbs up or thumbs down, or unmute themselves and answer this. All right, so let's work it out together. If there is oil, then 95% of the time that seismic says there is oil, seismic will say yes, there is oil. So that's the 95% accuracy here. But if we try to flip those probabilities, if we asked what's the probability that there is oil, given that seismic says there is oil, then using the simple Bayes rule, which most of us learned in school, we see that the probability actually reduces to 16%. And if we use those numbers right here to obtain the posterior value, we see that it's actually $455,000, which is less than the 500K, and hence it would not make sense to pay 500K. So this was very counterintuitive, because only with 5% decrease in accuracy, even half the cost was not worth it mathematically to pay. And for exploration problems, this is why I recommend a structured and quantitative approach to decision making, as opposed to simply using our intuition to say whether obtaining certain information is valuable or not. So this is one approach to thinking about it and then calculating the economic value in a structured way. So first you would want to ask and try to answer the following questions. Is this evidence perfect or imperfect? And does it affect our decision given all of the other data we have? And finally, even if it affects a decision and if it has the potential to change our decision, then is it worth paying for or not? Great. So how do we go about answering this question? And I propose with influence diagrams. Um, So what are influence diagrams? They are similar to Bayesian networks. As you see here, Bayesian networks had these uncertain nodes in the, circles, but in addition to the uncertain nodes, they have two additional things. One is a decision node denoted by square, and another is a value node denoted by a diamond. And in this example, let's say that our value is a convenience cost. So if it rains, I would want to carry an umbrella, but if there is no chance of there being rain today, then there is an inconvenience cost of carrying the umbrella. So in order to decide whether or not I should carry an umbrella today, I might look outside and see whether it's cloudy or sunny, or I might pay for an accurate weather report to make that decision. To represent the same decision in a decision tree, it would actually require many more nodes. So one, the decision tree does not, there is no apparent conditional dependence or independence relationship seen in this decision tree, which we can see easily in this influence diagram. A second is that the decision trees grow exponentially with the number of nodes. And in this case, all of these nodes had only two options, so rain or no rain. But if they had three levels or say multiple options, this tree would grow even more. And hence, when say if this team is handing out um, this value, say the probability analysis to another team, what they might do is instead of handing down this large tree, they might do a weighted average of all of these convenience costs and then hand down a single number, which would lead to a loss of lot of information. And then when this new team right here does certain analysis, it would be very hard to propagate that back to some of these, to re-inform some of these variables. And hence, influence diagrams might serve as a better tool for quantitative decision making. Now that we understand what influence diagrams are, let's go ahead and apply it to our basin. So in case of the John Dark Basin, Mobil first acquired seismic data in the basin in 1966. The first exploration well was drilled in 1971 and it flowed oil, and source rock was first sampled in 1973. The Hebron field, which is going to be our focus, was discovered in 1981, but because of the uncertainty in reserve estimates and high capital expenditure costs, it took them 20 long years to drill the first 5 exploration wells, and then the production only began in 2017. To demonstrate the application of influence diagram-based decision analysis, I'm going to use a Hebron-like prospect as the case study. And I will consider Hebron's geology and development history as a benchmark to my findings, but I will refer to my example as prospect A to refrain from offering differing decisions looking back, because that might just have hindsight bias. So it's also challenging to obtain all of the data and evaluations and exact timing of acquisitions, processing, and reporting over the 40-year development history of this field. And hence, as I said, we will be using this prospect A. which is in a similar place as Hebron and has a similar history as Hebron. We just won't call it that. Just to remind you where the Hebron field is, it's right here in the center of the basin. And this is the first 2D seismic that was obtained in 1981. And this is the 3D seismic that was obtained 2 decades later. From the initial 2D seismic, we see that we had some idea of fault blocks, but there was no direct hydrocarbon indicators. So now let's step back to the year 1981. This is the schematic of our understanding in the year 1981, where we know that there are fault blocks, there are 3 stacked reservoirs, because these are also what we've encountered in nearby fields that were already drilled. But some of the key uncertainties related to the reservoir deliverability in this part of the basin, the migration to this part of the basin, the quality of seal and biodegradation remain. The volume estimate then was 700 million barrels, which would yield a revenue of about $35 billion. Um, the cost of acquiring a 3D seismic over the field is presumed at $10 million based on the lower bound estimate for offshore Atlantic Canada. Um, and the cost of drilling an exploratory well is about $40 million based on the costs that I obtained from the Canadian Association of Petroleum Producers estimate. Um, Also, Hibernia platform, which is the other big field in the basin, has a gravity-based structure production platform, while Terra Nova and White Rose fields, the other 2 fields, are produced using an FPSO unit, the floating production storage and offloading unit. So the choice of the type of production facility would depend on the proximity to the land, depth and extent of oil and natural gas in the field, and anticipated production rates. And I evaluated that given the conditions we know about this prospect A, that it would require a GPS platform, and that would cost about $14 billion. And this is because both the Hebron and Hibernia are located in a high-risk area called the Iceberg Alley. And the cost of the Hibernia structure was about was about $6 billion, and then given the inflation in the cost of material and services in the past 15 years, I calculated the cost of the production platform for Prospect A at $8 billion. Then, along with the operation costs, the total came out to $14 billion. And this is just a view of that platform. And here's the influence diagram that represents the decision at hand. Um, the letter P is for the prospect. So within they are the 2 fault blocks, so prospect 1 and 2. The R, the reservoirs R1, R2, R3 are the stacked reservoirs. And whenever it says P1, R2, it means that the middle reservoir in the first fault block. So in addition to petroleum volume, quality is an important factor for economic analysis. So the oil's API gravity in degrees, which is inversely related to its density, is a unit that we use for quality. And given that we had observed biodegradation in a block in the Terra Nova field, we also consider biodegradation as a risk factor. I'd assigned a prior probability of 0.5, just half, given that we did not have any additional information. And if we discovered, if we sampled biodegraded oil in one of the fault blocks, we would revise the probability of biodegradation in the second fault block to 0.9. And if we did not, we would revise it to 0.1. Now to assign the prior and posterior probabilities to all of these other factors, we used the Milkov tables from his paper in 2015, which I will come to the next, show in the next slide. But to evaluate all of these, I use the expected net present value as the target variable, here value, to be maximized. And the use of monetary units usually is a good option in these cases because it permits different decision makers to consider the implications of choices in terms of a value scale of common experience. Then the price per barrel of oil given the API gravity is 50 per barrel for the sweet 30 to 40 degree API oil, and then 40 per barrel for 18 to 20 degree heavy oil. So now to assign prior and posterior probabilities, we use the Markov risk tables because they take into account both the data-derived and model-derived positive, neutral, and negative evidence for six geologic risk factors of the petroleum system, which are structure, presence of reservoir facies, reservoir deliverability, seal, source presence and maturity, and migration. And these also use some fundamental and relevant subsurface information and reduce the effect of biases and provide objectivity and consistency. Hence, we are using these tables. So we know that source, presence, and maturity was already established in the fetch area to the north of before exploration began in Prospect A. So source presence is not a risk factor. So of the six risk factors, I've shown example of the remaining two of the remaining five here. So if we observe a high relief structure in sparse 2D lines, then we can assign a probability of 80% to the presence of the structure for accumulation. While if you observe the same structure in 3D high quality seismic data, then we can be confident about the all-way closure or lack thereof. Similarly, the prior probability of good reservoir deliverability is 0.7 for Ben Nevis and Hibernia reservoirs, as shown in this table, but it is 0.55 for the deeper John Dark reservoir because of its deeper depth of burial and risk of porosity loss due to cementation. But if we were to drill an exploration well in this area, then we would be able to assign a higher confidence or higher probability to the reservoir deliverability risk factor, and that would say that's how the value of drilling an exploration well would be calculated. So when we do the calculation using the influence diagram that I showed before, we see that if we do nothing, our prior and posterior values remain at $0 million. If we drill an exploration well and we are able to reduce some of the uncertainties, we see that the value of information from drilling that exploration well is $483 million, which exceeds the cost of drilling that exploration well, which was $40 million. Hence, a rational decision maker with that who is risk neutral will go ahead and drill this exploration well. While if we did not do any additional evaluations, we just had some sparse 2D seismic and we went ahead and built a production platform, the expected value for this field would be a negative $7.1 billion, which sort of makes sense. No one directly goes ahead and builds a production platform without doing exploration and appraisal. So the exploration results show that as once we go ahead and drill this exploration well, these are some of the things we found. In the Hebron well, heavy oil was sampled, so we take into account the outcome from our outcome for our prospect A, which would be heavy oil, and then the reserve volumes are revised to 590 million barrels for the shallow reservoirs and smaller accumulation for the deeper reservoirs. And our revised expected value is now $17.4 billion given these new volume evaluations. And our next decision is whether or not we should appraise this field or we should abandon it right now after drilling the first exploration well. And when we do this analysis again, the value of information analysis indicates that our maximum spend for appraisal should be about $3.4 billion. And since this cost of appraisal is less than this cost, it would make sense to go ahead and do the appraisal. So this sort of different levels of decision making, from exploration to appraisal to production, are the posterior from one stage acts as prior for the next stage. And then also for different teams within a company, the uncertainties within their teams and their own values can be combined in influence diagrams because they are modular. So for example, in all of these evaluations, I assumed the cost of the revenue from each barrel of oil to be constant, but we know that there are many market variables and like geopolitical uncertainties. The team doing economic evaluations can still use the same model, and their evaluations can actually be informed to revise some of our geologic parameters using influence diagrams. And that's about all. Thanks to all of the industrial affiliates. Thank you.
Excellent. Thank you, Tanvi. I definitely want the influence diagram on when it's raining and when to take an umbrella. So thank you for that. You have a question. Tanvi, I kind of understand the math, but how do you determine if data such as seismics can be 95% certain?
Yes, so I think that number is quite hard to obtain, but I think especially for companies that have decades of data, um, that's something that would be very useful to go back and analyze. So
Yeah.
because we have results of what was actually encountered after what we saw, or after what we assumed. So I think these are some of the numbers that can be obtained later. But since I did not have access to that sort of a decades-long repository, I used the Milkoff tables, and I believe that the Milkoff tables are based on an evaluation like that. So something like 2D seismic being, say, 70% accurate for determining the risk related to the structure, while the 3D being much more accurate, is from some of the past data. And I used Milkoff tables in this case, and I think if a student were to start out, they could use the Milkoff tables because one, this data is publicly available. So like in terms of reproducibility, it would make sense. And for your companies, you could use internal databases.
Fantastic. Thank you. I am looking at the chat and also the tiny URL, which you don't see people typing into. So if you want to put comments and questions in there, you can. So it looks like that is the only question for you right now. If people want to stay on after Marcelo and Ken's talk for a few minutes, we can just take general questions. If I can ask all the students to stay on who presented today, we could do that. Maybe 10 or 15 minutes. And then the other thing is that affiliates, please feel free to arrange a breakout session with any of the students at your convenience. Okay, so with that, thanks, Tanvi.